Good morning, Professor Arif. Today we are going to present our group's exploration of a transformative technology in biomedical engineering, which is silicon-based avalanche photodiodes, advancements in applications in medical imaging. Next. These are our group members. Okay, my name is Jacqueline Fadil, and I'll be presenting section 1 of our group's presentation. Next. Okay, first one, why medical imaging matters. Medical imaging is one of the most important tools in modern healthcare. It allows doctors to see inside the human body without surgery, helping them diagnose diseases like cancer or brain disorders, plan treatments, and monitor how well a therapy is working. But here's the key point. Many of these imaging techniques rely on detecting extremely faint light, sometimes just a handful of photons. So the quality of the light detector used can make a huge difference in how accurate and useful the image is. Next. How is it used? Medical imaging is used in many critical applications such as early cancer detection, mapping brain activity in conditions like Alzheimer's or epilepsy, monitoring blood flow in the heart, and even guiding surgeries in real time. All of these depend on highly sensitive and fast light detectors to capture signals accurately and quickly. Next. Okay, the problem with current light detectors. Traditionally, two types of detectors have been used. The first one is photomultiplier tubes, PMTs, which are very sensitive and fast, but also bulky, fragile, and require high voltage. They also don't work inside MRI machines because they're affected by magnetic fields. And the second one is standard photodiodes, which are small, cheap, and low power, but not sensitive enough for very dim light, like the signals from deep inside the body. In short, PMTs are powerful but impractical for modern miniaturized devices, while standard photodiodes are compact but too weak for advanced imaging needs. Okay, next. This is where avalanche photodiodes or APDs come in. An APD is a tiny semiconductor device, usually made of silicon, that can detect even a single photon and amplify its signal right inside the chip. Think of it like a built-in volume knob for light. It takes a whisper quiet signal and makes it loud enough to measure clearly. Unlike PMTs, APDs are solid-state, compact, and compatible with modern electronics. Next, please. Why APDs are better for medical imaging? APDs offer several advantages that make them ideal for medical use. The first one is high responsivity. They can detect very faint light from deep tissues. Then ultra-fast response, which is critical for time-sensitive scans like time-of-flight PET. They also have compact size, enabling wearable or implantable imaging devices, low voltage operation, making them safer and more energy efficient, and importantly, they're MRI compatible since they contain no metal parts and aren't affected by magnetic fields. These features make APDs a practical high performance alternative that bridges the gap between traditional detectors.
Hey, my name is Bilal Chan, and now I'm going to explain the section 2 for the avalanche. So the first one is operating principle of APDs. What is photo detection mechanism? APDs convert light into electrical signals by absorbing photons in semiconductor materials such as silicon, germanium, or 3 to 5 compounds. When photons accept the bandgap energy, they create electron hole pair that are accelerated by a strong reverse bias field. Through impact ionization, more carriers are generated, producing the avalanche effect and amplifying the signal. And how the APD detect lights? The first one is incoming photons are absorbed by a semiconductor material. If photons energy, the second one is if photon energy exceeds the band gap, it generates an electron hole pair. The third one is a strong reverse bias electric field accelerates these carriers. And the last one is accelerated carriers collide with atoms, which is generate more carriers. The next is avalanche multiplication effect. In an APD, carriers moving from the I layer into the high field P layer gain enough energy to create additional electrons, causing rapid charge multiplication known as avalanche amplification. The strong electric field near the p-n junction maximize this process, significantly increasing signal strength compared to conventional photodiodes. And the avalanche multiplication effect is this generation is called impact ionization, and then second one is results in rapid multiplication of charge carriers, and the third one is produce a strongly amplified electrical signal from a single photon. The next is avalanche gain and responsivity. Avalanche gain is defined as the ratio of total generated charge carriers to the initial photo-generated carriers, while responsivity is measures how effectively incoming optical power is converted to the electrical current and expressed in A or W. The next is the noise characteristic in APDs. APD performance is affected by three primary types of noise. The first one is dark current noise, which is caused by thermally generated carriers even in the absence of light, producing a baseline current. The second one is thermal noise, due to the random thermal motion of charged carriers, limiting the signal to noise ratio. The third one is excess noise, inherent to avalanche multiplication, resulting from fluctuation in the multiplication process and degrading timing performance. These noise sources are measured in noise current density and must be minimized for high-quality imaging and accurate detection. Next is timing resolution. What is timing resolution? Timing resolution refers to the ability of APDs to precisely detect the time of photon arrival. Timing resolution equals to ability to detect exact at time of photons. Why it matters? Because it's essential for time of flight system like improves spatial accuracy and image clarity. The APD performance is picoseconds to nanoseconds, influenced by carrier transit time, material quality, and circuit design. The result is enable high-speed imaging and precise analocation. Next is performance comparison. This is the comparison between APDs, conventional photodiodes, and PMTs. For the responsivity, APDs get a very high due to avalanche gain, while conventional photodiodes is moderate and very moderate, and the PMTs is very high. And we go on to the timing resolution. The APDs is excellent. The conventional photodiodes is moderate, while PMTs is excellent. And the next one is magnetic sensitivity. APDs is not sensitive, while APDs and conventional photodiodes is not sensitive, while PMTs is sensitive.
So next is the section 3. APDs outperform conventional photodiodes in responsivity and detection efficiency due to internal amplifications. Compared to PMTs, APDs offer similar thing performance, but with lower voltage requirements, compact size, and better long-term stability, making them more suitable for portable and modern imaging systems. Medical imaging applications of APDs. APDs are widely used in PET, SPEC, and tough PET because they can detect very small amounts of light with high sensitivity. Their fast response and low noise help improve image clarity and overall diagnostic accuracy. These features make APDs a core component in modern nuclear imaging system. So what is PET? PET is positron emission tomography. It visualizes metabolic activity by tracking radio tracers such as FDG18 inside the body, and positrons emitted by tracer annihilate with electrons to produce two gamma photons traveling in opposite directions. By detecting these photons, PET creates detailed 3D image to assess cancer, brain function, and cardiac performance. How IPDs function in PET systems. Gamma photons first hits scintillators crystals, which convert them into faint flash of light. IPDs detect this light with high internal gain, producing clean electrical signals. Their low voltage operation and MRI compatibility support compact PET and MRI hybrid scanners. PET image improvements using APDs, higher sensitivity, improved detection of low intensity scintillation light, reduce noise helps sharpen edges and reduce image blurring. Better photon captures leads to increased contrast and more reliable lesion detection. What is SPEC? SPEC use gamma emitting tracers use STC99M and rotates a camera around the patients to reconstruct images. A collimator selectively filters incoming photons to determine the directions, and it is commonly used for cadaveric imaging, brain studies, and organ specific functional assessment. So how IPDs improve SPEC performance? IPDs enhance energy resolution, helping the system distinguish photons energies more accurately. Their small size enable compact modular camera designs for dedicated SPEC system. Improves responsivity, contribute to higher contrast and better structural detail. Time of flight of PET. TOF PET measures the slight difference in arrival time between the two annihilation photons. This timing difference narrow the possible location of the event along the detector line. This reduces noise and speeds up image reconstruction with better localization. Why IPDs are essential in TOF PET? IPDs over nanoseconds level timing due to fast avalanche multiplications. Accurate timing improve SNR and makes most lesion easier to identify. High timing precision also lowers the required tracer dose for patients. Scintillator plus IPD detector. Scintillators convert incoming gamma radiation into visible light. IPDs amplify this light efficiently, providing stable and accurate signals. This pairing boosts detection efficiency, timing performance, and overall image quality across SPEC and SPEC systems. APDs improve sensitivity, timing accuracy, and noise performance in the nuclear imaging system. They enable clear image and better spatial resolution in PET, SPEC, and TOF PET. Their compact and MRI safe operations support the development of hybrid and portable imaging devices.
Section 4, covering additional applications and guardrails. Okay, so first of all is computer tomography. So these basically use X-rays to scan a body. The problem is X-rays have high radiation, and thus the high photon detection density of APDs allow less ionizing radiation. Next. Fluorescence imaging uses fluorescent light from molecules or probes to detect and image the molecules. The advantage here is that because they're weak fluorescent signals, the high gain of APDs allow these signals to be further gained. Next. OCTs uses light from a sample arm and a reference arm, backscattered light to create an image. The next thing about the high gain characteristics of APDs enable the detection of those weak optical signals. Next. And now, this is the next part, basically, for how do we protect from noise, from current, and all that. So the thing we want to use is group 4 elements, such as silicon and germanium, because group 3 and 5 elements have their own disadvantages. Next. The crucial components of SPADs is the guard ring, which plays a significant role in preventing premature edge breakdown, optimizing electric field distribution. Since, of course, they have an avalanche multiplication effect, it's important that we don't make it so that a noise or some kind of interference causes a multiplication effect, or else the noise is going to be even more amplified. Next. The P-well guard ring. As you can see in this picture, there are P-wells next to the absorption region and the amplification region. That is the guard from noise or charge carrier being accidentally triggered into the multiplication area. Next. These are some other guard ring advances. One of them uses a physical guard ring, and the other one actually has a virtual guard ring, which is created with a unique gradient doping profile, where basically the deeper it goes into the wafer, the stronger the doping profile is. Next. Now, this is a new invention, which is basically the absorption area is created by germanium, and then the multiplication area is by silicon. The unique advantage here is that it allows detection of IR lights or lights on a lower energy level, or I guess a higher wavelength. Next. In this instance, you can see that there's a charge sheet in the middle of the amplification area and the absorption area. This charge sheet lowers the electrical field on the absorption region and increases the electrical field on the amplification area. Next. There are quite a few manufacturing prospects of APDs and SPADs, since the nice thing is that they use CMOS technology, which means they can be well integrated into already existing technology. And also, there's a lot of manufacturers for APDs and SPADs. And they cover a wide spectral region and optimize for all sorts of biomedical applications, as you've seen on part 3. Next.
Okay, to summarize everything up, next. First off, we have the current challenges for silicon APDs. First off, the cost. Silicon APDs and SiPM arrays require precise CMOS compatible fabrication, and advanced processes increase manufacturing costs. So this will increase the costs. And for scalability, scaling to large area arrays require uniform avalanche behavior and consistent breakdown voltage across thousands of microcells. And the process variations can cause non-uniform gain, affecting image consistency in PET/FET. And next is the noise. Dark current, thermal noise, and excess noise from avalanche multiplication still limit low light performance. And the interfaces like SCI boundaries can inject carriers and increase dark counts. Guard ring optimization is required to suppress premature edge breakdown. And for optical crosstalks in SiPM type architectures, avalanche events in one microcell can trigger neighboring cells, and crosstalk degrades timing resolution and energy discrimination, which is critical for TOF, PET, I mean. And for the integration complexity, APDs have to require with scintillators, readout ASICs, cooling, and power management. Maintaining stable bias, minimizing temperature drift, and ensuring consistent gain across arrays at system level complexity, and hybrid systems require careful electromagnetic and thermal co-design. Right? So for the future perspectives, we have low light performance, improved guard rings, doping profiles, and germanium on silicon layers boost the detection system. For multispectral or NIR imaging, SIGE or germanium on SI structures extend detection into NIR for deeper optical/functional imaging. And we can also make portable and wearable systems. And we can do photon number resolving SiPMs. Next-gen SiPMs can count photon numbers per pulse, which improves quantitative imaging. And we can also do AI/ML integration, which enhances noise filtering, event classification, detect calibration, and TOF-PET reconstruction. And there's theranostics and image-guided therapy. High sensitivity supports real-time surgical guidance, targeted drug delivery monitoring, and hybrid optical nuclear imaging. Next. So in conclusion, silicon APDs and especially SiPM arrays are becoming the default detectors for modern biomedical imaging. Their sensitivity, timing, precision, compactness, and CMOS compatibility align perfectly with trends in hybrid imaging, AI-driven reconstruction, and portable diagnostics. Though challenges remain, rapid progress in silicon engineering continues to strengthen their role in high-performance, next-generation medical imaging systems. that is all for our presentation. Thank you for listening.